bit of a problem with the Mann Whitney. You definitely need to have version 26, because if you don't have version 26, you will get your Mann Whitney test wrong. Because SPSS, being a lovely piece of software, has decided to completely change the way it works out Mann Whitney tests. Yip-de-doo-dah, thank you for that. So the new way of doing it looks completely different and actually gives you completely different answers to the old way. The p-values are the same. The test statistic is just like, where did you get that from? And I will explain in a minute where they got it from after me taking 2 days to work out where they got it from, which was annoying. But anyway, to do this, it's an example of a non-parametric test. So you go to non-parametric tests. These are two independent samples. So it's an independent samples test. The independent samples in, this is the post-crawl data from the size of periwinkles. They're independent in that the size of the periwinkle in one location, the midshore, is not affecting the size of periwinkle in the lower shore. They're not related to each other. Well, they might be genetically related, but let's ignore that and pretend they're just randomly sampled lengths. Now, to do this, this is a wizard. And an example of a wizard, there are some other statistical programs that use wizard-based tools, for example, GraphPad Prism. And the idea of them is to guide you through it so you don't have to think. So the thing about this wizard is it's pretty much going to do everything automatically unless you do something silly like click on I want to do things myself. So if you don't know what you're doing, let it do it everything automatically. So it says, do you want it to do it automatically? Yes, you do. If you really know your statistics and your way around SPSS, then you can click on customize analysis if you want to, or compare medians. It's actually going to do compare medians. Next thing, it wants the fields. So it wants to tell you which columns of data are actually important for this calculation. Now, I've given you a data set that only has 2 columns in it. If I gave you one which had 50 columns in it, then it'd be a bit more selective and a bit more thought going into it. But there's not a lot really. Now, even more than that, the 2 variables, only one of them is numeric. So the numeric thing is the thing that I'm going to need to do a test about. So that's height. The thing that the grouping variable is the zone. So you can tell if you've got version 26 installed, because it's the only one that you should get from, or 26 or above. It's the only one that you should be getting from the university website. It's the most up-to-date one. You'll know, I'll show you in a minute that you know if you've got 26 installed, because if you had 25 installed, the output would not look like what I'm going to show you in a second. So groups, zone. That's it. I've told it which columns of data I need it to think about. I can go to settings, which says, do you want to automatically do things, by me figuring out, well, SPSS being me, figuring out what you want to do and doing it automatically for you, or you can click on customize. Now, as I said, if you don't know exactly completely what you're doing, don't touch anything at all. Zone represents the zone of the shore of the data. So if I clicked on view value labels, lower shore, mid shore, it's where on the beach I picked up my shell. But it's not particularly important. It's just a grouping variable. So you press run, and that is it. Absolutely, there's nothing else. Done. Absolutely got this Mann Whitney. I haven't needed to do anything at all other than say, do things automatically. These are the 2 columns of data I want to. Done. Now, if you had a version that is not version 26, you would only get this table. It would be in, it tells you that, so it looks exactly like this. If there's a significant difference where the p-value is less than 0.05, this would be colored in yellow and it would say reject the null hypothesis. But under the old wizard, this is the only table you had. Yes. So here the p-value is 0.429. which is exactly the thing that's in here. And the test statistic is Mann Whitney test statistic, which is 230. It also gives you a couple of plots and everything else. Now, for some absolutely unknown reason, which I can't fathom in the slightest, people are doing this. They're going to non-parametric tests. They're going to legacy dialogues. Like, why? Legacy means old-fashioned, no longer needed, waste of time, don't use it. That's why it says legacy. It's left over from the way people used to do it before they learned not to do it that way. Legacy servers are the things that you don't want to ever use in your life. So don't use legacies. So you go to legacy and go to 2 independent samples, which you have to know a much higher level of statistics to understand that it's 2 independent samples. Exactly. Whereas if you do, it's very hard to do it using the legacy. If you use the wizard, it's like a piece of cake. You go into here, and again, you have to pick the test variable, and it's going to be heights. Then you pick the grouping variable, and it says zone. Now I have to go through another process of defining the zones, which are going to be called 1 and 2. And I do continue. Then it gives me options. I can say, is it a Mann Whitney, is it Kolmogorov, Moses, or Wolfowitz? Well, I want to do a Mann Whitney. But you see, these are all decisions. The wizard took all those decisions away from me. I didn't have to think about them. I press OK, and it gives me the wrong answer. So you see here, here's the p-value, 0.429, exactly the same as it is in this table, which is what you got from the old version of the wizard. You just got the table. Here's the sum of the positive ranks, some of the ranks for the lower shore, some of the ranks for the mid shore. 380, 440. So the test statistic, according to this, is 170. But the test statistic, according to this, is 230. Now, how does that happen? This took me 2 days of working out what the hell was going on between those 2 calculations. Like, how? And why and what is happening. So don't use the legacy. Just use the other one. It's a piece of cake, gives you the right answer. When we originally did it with the original wizard, you just got that table and you didn't get this table at all. So you didn't get this more detailed analysis. So in past years, the only thing I asked about was the p-value. But because they've given me this nice new table, I thought, oh, I lost the test statistic. So I did all the test statistic calculations, and the way I do my tests to automate generating them, I can't automate the process of creating data in SPSS very easily. So they're all created in R, and R runs through and creates the output, and it gives me a number which is neither this one nor this one, which really didn't help me an awful lot, because I'm going, wait a minute. So SPSS has the Mann Whitney U and says it's 170 in the old version, and the Wilcoxon W, which he says it's 380. In the new version, I got 230 and the W is 440. Like, these are completely different numbers, and they're not the same as the W I'm getting out of R either. So I've got 5 different test statistics coming out of this for the same set of data. What on earth is happening? No, the p-value is 0.429. It's not 0.427. It's an exact significance test, not the asymptotic test. This is the one in that you can see in the summary of the hypothesis test from the wizard. It tells you exactly what p-value is wanted. This one is not. This one assumes that the data is normally distributed, and that's why it's called asymptotic. So it is a tendency towards the p-values being normally distributed. This second one, the 0.429, is when you actually calculate the probability of that particular distribution of data. So this also adds to confusion by giving you two significance, one which is wrong, one which isn't. Stand for the standard way of calculating your p-values for the chi-squared, it is labelled asymptotic sig. But this time I want the exact. But the reason was I wanted you pretty much to look at this test summary thing. So that one, because here it's summarized very easily, and then here you get a much more complicated table. So here's your p-value. So then you look at this table and go, okay, there's my p-value, and this one's just something else that I don't care about. So this is the p-value for having a z value of this. But let's see what I mean. Every time you can do it at the simple level, or you end up having to go to a massively more complicated level than you need to. So trying to be simple sometimes ends up not being. So I spent a lot of time, therefore, trying to pull apart what the hell SPSS is doing. So I wrote a new set of slides about Mann Whitney test in SPSS. So it's an example of a ranked test. So imagine you have a sample of 10 heights for two groups. And you have 10 shells instead of, I can't remember how many are in this post-crawl ones, there's more. So I've got 10 heights for two groups A and B. Null hypothesis is there's no difference in the heights in either between group A and B. You rank all of the heights to create numbers which go from 1 to 20. The null hypothesis should say most likely true. Let's go and redo it. So is most likely true if the sum of the ranks for A and B are the same. So if you total up the amount of ranks and total ranks of the numbers from 1 to 20, total those up and you halve that and you split it between the two groups, then this is when it's most likely that there's no difference between the two groups. So the sum of the ranks for the group A is exactly the same as the sum of the ranks for group B. The difference is 0. Any deviation, so there's a difference in the sum of the ranks between the two different groups, suggests that they might not have the same median height, but you don't know exactly how strong that difference has to be before you know it's significant. So the strongest possible evidence would be if all of the numbers from, so you've got your two groups. They're ranked 1 to 10 and then 11 to 20. So if you have all the ranks 1 to 10 in group A and all the ranks 11 to 20 in group B, that is the maximum possible difference you can achieve. So the sum of the ranks 1 to 10 is 55, sum of the ranks 11 to 20 is 155. So the maximum potential difference between the sums of the ranks of the two different groups is 100, and the minimum, which I just showed you, is 0. There's a quick thing here to show you how I did the sum of the ranks. So 1 plus 10 is 11, 2 plus 9 is 11, so it's 5 lots of 11 pairs that add up to 11, and it's 5 lots of pairs that add up to 31. That was just an aside because I was doing some mental maths. So what is SPSS doing to calculate that damn Mann Whitney and W thing? So for the U, it calculates the maximum difference between the ranks of the two groups, and then it subtracts the value of W that I find in R from this. Now W in R is the difference between the smallest sum of the ranks and the average, so the average sum of the ranks. So if I total up all the sum of the ranks, divide by 2, that would be, and if both groups had that number, then the two would be have equal sum of ranks. So the difference between the two would be 0. W is calculated by looking at how much the sum of the ranks deviates from that average. That's what W means. in R, but W in SPSS is not that. What you do is calculate the most extreme value, which is that 100, and then look at how much you deviate from having no difference and take that away from that 100. W is much easier. You calculate the sum of the ranks and pick the largest, or in the old version, the smallest. So let's go through all of this mumbo jumbo in an actual example. So I've got a data set, which is the butterfat data set, which you will come across soon. So I've got the butterfat data set. When I calculated it in R, the W value for the test statistic was 25, the P value is 0.06301, N1 equals N2 equals 10, the maximum difference of the ranks is 100. I've demonstrated that already for something when you've got two groups of 10, in total you've got 20. I took the set of data that I had got and I decided to do it by hand. So I popped this into Excel for a minute, reordered all the sizes of the butterfats, put their ranks, reordered them back so they're ordered by their groups, summed up the value of the ranks for group 1, summed up the values for group 2. So the total sum of the ranks for group 1 was 80, the total sum of the ranks for group 2 was 130. If I add those two numbers together, it gives me the 210, which is the 55 plus the 155. If I divide 210 in half, that means if each of the groups had the sum of the ranks, which was 105, they'd be even. There'd be no difference between the two groups. So that is a perfect example of my null hypothesis. There's no difference between the two groups because their sum of the ranks is 105. So 105 minus 80 gives me 25, or the difference between 105 and 130 is 25. It doesn't make any difference which way you do it. The difference between averaging those ranks out equally between the two groups and what you actually observe is 25, which happens to be what R is calculating as the value of W. So that's how W is calculated. It's based on the difference between splitting the ranks equally between the two groups and what you actually observe. Then I go to SPSS in the wizard and I find that their value is not 25, it's 75. I'm going, where's this come from? Now, as I told you, the maximum possible difference that you could get between these sets if all of the lowest ranks were in group A and all the highest ranks were in group B would be 100. So that 25, if I subtract that from 100, I get my 75 that's here. So that's telling you how much away you are from the maximum possible difference. So I'm 75 ranks different from the 100, which would be clear evidence demonstrating absolutely that the two different things have different heights. So that's telling you how far away you are from the best possible hypothesis for a difference, whereas the 25 is telling you how close you are to the two having the same number of ranks. It's a bit of a and then there's Wilcoxon, which is 130. Now if you look at the previous thing, 130 is just the sum of the ranks of one of the groups. It's the biggest of the two. It's not rocket science to work out what the W is. That's done. The other one, right pain in the neck. Next thing, I lose the legacy dialogues and I get 25. Yay! The Wilcoxon is 80. So you see what SPSS has done is moved from using the sum of the ranks, the biggest of the two, to the smallest of the two. And it's moved from using the distance from the mean to each of the values to from the extremes to the values. So it's just reversed the way it does the test. Working out the probability for it ends up exactly the same. So the p-value is 0.063 if I use the legacy dialects. The p-value is 0.063 if I use the wizard, and the p-value if I use R is 0.063. So the p-value is always the same, but the test statistic is all over the place depending on which method you do it. So SPSS has changed from using the smallest sum of the ranks to the largest sum of the ranks for the W, and SPSS has changed the Mann Whitney test statistic from measuring the distance from the mean of the ranks to the measurement to the most extreme possible difference in the ranks, and confused everyone in the process. The test and all the answers assume you use the wizard on version 26, because the wizard on version less than 26 will not give you a table including the test statistic at all.